determinant you want to look at, or one of those equations where you have to multiply by the inverse?
The equation one.
With the inverse in there?
Yes.
Okay, so again, remember that you're really modeling it after something like this. So if you have a number times a variable equals a number, as opposed to a matrix, times a variable equal a matrix. All right? So notice that they're kind of similar, and that here you're solving for a matrix, here you're solving for a number. Now here you'd normally divide, but to make it seem similar to this, we're going to take division off the table because there's no division with matrices. Okay? So over here, if you were to want to get rid of x without division, you would multiply by a 1/3. And a 1/3 is actually we call it a reciprocal, but it's really the multiplicative inverse. So it's actually similar in that regard. You'd say, all right, I'm going to multiply by a 1/3. Now, with numbers, I can, like if this was a equal a, I could multiply both sides by a third. But in doing that, I would be exercising the commutative property, which is great with this, bad with this. Okay? So here, really, if I want to model it like this, I would have to say, okay, if I have the same number on both sides, which according to this it is, I know it looks different, but they're saying that's equal to that, I would have to put the 1/3 on the left of each side if I wanted to treat it like a matrix. So let's come down and just fill it back in. So essentially, you'd be 1/3 by this and 1/3 by this, right? So the way this is linked to that is here, my 1/3 was my multiplicative inverse, right? So here, I would have to find the inverse of that, and I would have to put it on the left side of this, and I would have to put it on the left side of that, kind of like I did here. Drop this stuff down, inverse on both sides. So what is the inverse of this?
3.
So switch the 3 and the 2. Negate those two things. And then one last thing that's part of the inverse also is what?
1
over
6 plus 5. So
6
11.
minus the -5 or plus 5, which is 11. So all of that's the inverse, but I don't really like multiplying the 1/11th in because then I'd have to multiply with fractions, and that's a little annoying. So I'm just going to wait on the 1/11th, but I put that same number over here. Every now and then I get somebody takes the inverse of this and puts it down there. But that's not what I did here, right? I took the inverse of that and matched it. So the inverse of this matched it. And then all I have to do now is just bring down all of that. And then bring down this. Now, a lot of people are kind of lazy, and I'm not saying lazy in a bad way. If you were solving this, a lot of people just go, x equals 1/3 of 15 is 5, and they just want to know this part right here. And they skip this step, even though technically 1/3 times the 3 is 1, and 1x times x is x. What I'm going to be putting here on the left, this is like 1/3 times the 3 is going to give me 1, but it's really not 1, it's the what?
It's the 1 0 0.
It's the 1 0 0 1, the identity matrix. And it actually takes me a couple steps to get there. Because when I actually do the multiplication of these two things, I actually don't get the identity. Initially I get what? 6, 5,
And then
-3, 3, -10, 10, 5, 6. But when I multiply by the 1/11th, I get
1 0 0.
the identity. And the x is just dropping down all along, right? And then finally, what's the identity times x? X. So all I've really done on the left is show all these little steps, which you knew were going to happen anyway. But the upside of it is, I don't think many people have issues multiplying by a reciprocal. But some people do have issues finding the inverse. And if I don't check this, which is okay, if you're somebody like, I just don't make careless errors, I'm really good, I make A's on all my tests, I'm going to be fine. And a lot of people just skip this and just put the inverse there and find their answer. Because this is going to happen every time. Just like you know when you multiply by reciprocal, that's going to happen every time. But the nice part about this is a little harder than a reciprocal, and you get some feedback. Oh, I did do it right. So that confirms to me I picked the right inverse. The most common mistake I see on problems like this, people forget the 1/11th. But they don't check this. Like they might set it up and just go X. But if they had done the math, what would they have found? Wait, that's not the identity. Why is that not the identity? And then maybe it rings a bell and they go, oh, I forgot that fraction. And they do the determinant, figure that out, and go, oh yeah. And if they forget it there, they're going to forget it here too, right? So their answer ends up being off. So I use this as a check. But if you're one of those that doesn't make a lot of careless errors, like I don't make tons of them, you might see some of them from time to time, but especially if I was taking a test, I'm going to check my work. A lot of times I'm just hurrying up here and I'm not taking time to check everything. But if you're one of those that doesn't make a lot, yeah, you're welcome to skip this. But just be careful that you're right. Or maybe take your answer and plug it back in there and see if it works. Okay? So at this point, all I got to do is bring down the 1/11th and start cleaning this up. So rows times columns, 3, -4,
-1,
6, 5,
11,
-5, -8,
-13,
and -10, 10.
0,
And then all you got to do is multiply the 1/11th in.
-111,
So yeah, -1/11, 1, and 0. So if you had skipped all this and you said, you know what, I'm just multiplying by the inverse, I'm just going to put it there, save all this junk, you really might just go, okay, let me just check this. Plug that in there, multiply by that, and see if it actually gives you this. So the check might be as good, but I would probably encourage you, if you tend to make errors or maybe a little rusty on stuff, you get some real quick feedback on if you picked your inverse right. Anybody else on anything we've talked about so far? Okay, so yesterday you guys were watching the video from this class, and we got through a couple of little diagonal tricks. You remember those? And we found, even though I didn't prove it for all of them, we found that whenever you have zeros below a diagonal or above a diagonal or both, then you really don't have to do expansion by minors. What could you do?
Just multiply all the
Multiply the numbers in the diagonal. That's if the diagonal goes down to the right. So what I want to talk about today is what happens when it doesn't go down to the right, what happens when it does all kinds of weird things. So I'm going to get to that, but I actually don't even know if I'm going to do it first. Jump to page 60-something, and let's take a look. I'll give you the page and stuff. It says properties of determinants. It might be 70. 67. Yes. So jump to unique properties of determinants. And we're going to talk about these for a while. This is Math King land that we're venturing into. You go to math tournaments, they don't ask a whole lot of questions about stuff that's real life. They always are trying to trick you and mess with you and get you to assume the position or whatever. So we're going to be talking about what they're going to do and how we can beat them at their own game. And these usually are easy points for us. And I think you'll see that. So the first thing I want to talk about is being careful about multiplying a number outside of a matrix versus a number outside of a determinant. Now, a number outside of a matrix, what did you do? We did this day one. You multiply it by everything, right? I have a question. If I did have a number outside of a determinant, what's the motivation for multiplying it in? Here I needed to, and I'm done. But if I multiply it in, all of a sudden my numbers are bigger. So there's really no motivation, I think, to do that, because we're trying to get the value of this and then multiply by 5. If I put a 5 in there, it's just going to make my process harder. But the difference is, here, I don't multiply it into all 4 terms. I only multiply it into a row, any row, or any column, but not both. So rather than even do that, though, I don't think there's any real reason why you would multiply something in. But the reason why I mention that is this. Well, maybe I didn't even mention it here, but right here. What if I gave you something like this? And I said, evaluate the determinant, and you don't have a calculator on you. Actually, let me make one of these negative right here. Okay? Yeah, if I had this, it's going to be enormous numbers. 144 times 120. Okay, you're over here writing it out and multiplying like you were in 4th grade or whatever. And then you got to go that times that and change the sign. It ends up being a very tedious problem. But with determinants, if I had a scalar on the outside and I multiply it into one row or one column, doesn't that suggest that I could take something out of a row or out of a column? And what number do these have in common?
12.
And even more, think it bigger. 72 or 24, any of those would help, right? If you took a 12 out, you'd have a 12 and a 6. That already sounds better. If you take a 24 out, you have a 6 and a 3. But if you took a 72 out, now you have a 2 and a -1. That's a ton better looking. What about the bottom? Took a 120 out. Now you have another 2 and a 1. And heck, if you wanted to, you can take a 2 out of the column. But at this point, what have I done? I've made it where this determinant's going to be a lot more manageable. And I can go 2 minus a -2, so 2 plus 2 is 4. And now I have 120 times 72 times 4. Now I still have a little bit of multiplication to do, but I personally would rather just multiply that together than have to multiply that times that,
Wait,
and then that times that.
but if you pulled it out of the column, wouldn't it just be 2 times? Oh, but then it'd be, okay, I see.
Yeah, I did the 2 times 1 is 2,
Because it'd be plus.
minus a negative. So at this point, I would rather multiply this together. I don't know about you, but I would rather multiply this together than have to do that times that, minus that times that, and then add them together. So to me, it seems a little more simple. Now, don't forget these numbers when you take them out. But remember, when you factor out of a determinant, you factor out of one row or one column, right? But you don't factor out, like I don't need to go in here and go, oh, well, all I got to do, all I have here is a common 12 out of all 4. Don't do that, right? If you take a 12 out of all 4 of these, you mess it up. Because really, that's like taking a 12 out of the top and a 12 out of the bottom. So take it out of one row or one column if it helps you. And I usually throw a problem like that on the test, where just I give you a big 3x3 and the numbers are big, and you're like, what? It's going to take me forever. And you go, wait a minute, I can take a number out of that column, or I can take a number out of that row and make the numbers better looking, and then it makes it a little bit easier on you. You with me? Or heck, look at this, another little strategy. Sometimes it might even be better, maybe not. Like, what if I just took a 120 out of this? Are you with me? Now, what do I end up with? Even if I didn't take anything out, 144
Minus 144.
minus a negative 144?
Yeah.
So 144 plus 144?
Yeah.
288? So sometimes, even just taking it out of one row might make the math easier. And again, I'm still going to have to multiply 12 by 288 and put a 0 at the end. But it would maybe help you get there more quickly. And if you think about a ciphering question, it's all about getting there in time to maximize your points or whatever. So that's something I wanted you to see. I also want to talk about Gaussian-Jordan elimination. Now, it's a fancy word, and I don't need you to know necessarily right now what that word means. But I need you to know this process. So there are some rules, like everything in math, that apply to different things. All right, and I'm going to show you this. Like right here, I've got 2, 3, 1, 4, 5, -2, 3, 6, -7. And trust me, if I were to do the determinant, you get this. All right, now I want you to look at this. Right here, I'm going to look at this, and I'm going to add the first and the second row together. And what would that give you? 6, 8, -1. And when I add those two rows together and replace either one of those rows with the result, looks like I replaced the top row with the result, I still got 29, trust me. Now, that's not a proof, but that's an example how, with Gaussian-Jordan elimination, you are allowed to take any two rows or any two columns and combine them together. Just add whatever you see together and replace one of them with the result. Now, you may go, why in the world would you want to do that? That looks just as weird as this, right? And you're right, I would never do that here. But what if I had this? What if I had a big, let me see if I actually put one on here. No, let me just show you. What if I had something like 5, 3, 3, 3, negative 4, negative 3, negative 3, negative 3, 1, 7, 3, negative 1, 5, 2, 0, 6. Now, who wants to do a 4x4? What did we find out yesterday? When I go to do a 4x4, if I expand by a row, I end up having 4 what? 3x3s. That's a lot of work. But wait, what if I took Gaussian Jordan elimination? Basically, picked these 2 rows and added them together. What do I get? 1, 0, 0, 0. And then maybe, does that make sense? And then replace one of the rows with the result. Now what do I have? Now I just got to do 1 3x3. And it really made my work easy, right?
Yeah.
And sometimes you even see stuff like this. Like, what if this had been the case? I get to 1 3x3, right? So I end up going 1, and I change these numbers on you, but what if I had done this? And then you got down to here. What does this tell me? Wait, what if I were to add these 2 rows together? What would happen? 0, 0, 0. What happens if I expand by a bunch of zeros?
It's 0.
I would get 0. Does that make sense? So that would mean this whole thing is just 1 times 0, because if I add these 2 together, so this whole thing ended up being 0. And I didn't have to even do a determinant, right? I just knew some properties. Now we're going to walk through some of these so you can memorize them, but they all come, these properties I'm about to show you, almost all of them come from the idea of Gaussian Jordan elimination. So it's probably easier to remember the little trick than to actually go through this process, but they all are based on the idea that if you add 2 rows together, or if you factor something out first so that you can add 2 rows together, then you're going to get some simpler options when it comes to doing a determinant. So let's just take a look at some of these. Okay, what if any 2 rows, and I just mentioned this, what if any 2 rows or any 2 columns were total opposites? Then what happens when you add them together? You get 0, 0, 0, 0. And what happens if you have a row of zeros?
Then there's no, it's already 0.
It ends up being 0. Why? Because if I expand by this, I'm going 0 times its minor, doesn't matter, it's 0. 0 times its minor, doesn't matter, it's 0. Are you following me?
Mm-hmm.
So if this is a rule for you. If you ever look at any 2 rows that are opposites, or any 2 columns that are opposites, because you could do the same thing with columns. You can add 2 columns and then replace a column. If that happens, you know that you're going to end up with 0, because this is what would have happened in the elimination. Now I'll go one step further. What if they're the same? So that was your first property. Well, what if they're the same? Well, if they're the same, don't you have the right to factor out something, but just out of a row or just out of a column? So what if I factored out a -1 out of, say, row 2? Wouldn't that give me this? Now, I still have the -1 out there. I can't just dismiss that because I factored it out. But wouldn't that leave me this? Well, didn't your other property just say if you ever have any 2 rows or any 2 columns that are opposites, it's going to be 0? Right? And what's 0 times -1? 0. So do I have a new property now? Not only does it work if they're opposites, but with this process, it would also work if they're the same. So chalk that up to another rule. If you ever see 2 rows that are the same or opposites, this whole determinant is equal to 0.
So if you were to work out that determinant, it would be 0.
Yes, it'd just be a lot of work. Yeah. Okay? What about this? This is another thing that's not as used, but I want to talk about this. Take my word for it. I give you this, and I get 29. Now, I am going to interchange row 1 and row 2. So I'm going to put the 2, 3, 1 there, the 4, 5, -2 there. And I end up with -29. Are you with me?
Mm-hmm.
And then, if I interchange this one, column 2 and column 3, there's column 3, column 2 right there, I'm putting it there. There's column 3, I'm putting it there. What happened from that to this? Change signs again. So, do Do you think you come up with the rule? What happens if I interchange any two rows or any two columns?
You have to multiply them.
And by the way, they're adjoining. They have to be adjoining. If I change any two rows or any two columns, what does it do to my answer?
It makes it negative.
It negates it. And because I had two interchanges, now I can't switch these like the first and the third. To do that, I'd have to switch first and second, and then I'd have to switch second and third, and then I'd have to go back and switch these. Like for instance, it'll make better sense if I have this. What if I had a bunch of A values and B values and C values? And I want C's on the top and A's on the bottom. First I'd have to, and say this is all equal to, I don't know, let's say it's all equal to 10. If I switch the A's and the B's, what does that do? That puts B's on top and negates it, right? And then if I switch A's and C's, it negates it again, right? And then if I want C's on the top, because that was what I mean if I switched the first and the third, the B's would go back to the middle, C's would end up there. That negates it again. So even though in this particular, it just looked like I switched those two and negated it once, I really had to make 3 switches to get that to happen because the rule only applies to adjoining rows or adjoining columns.
Is there any situation where that wouldn't work? Switching the top and bottom?
Yeah, if it was first and fourth.
Oh, right.
Yeah, because the first and fourth would require an even number of switches, and then you'd end up with positive. But you would see that, but I'm going to show you little shortcuts for this kind of stuff. But this is how this mentality will show up. Check it out. Let's just say I told you that this ugly variable matrix is equal to 10. So you would just have to take my word for it, okay? You have no idea what A, B, C, D, E, F, G, H, I are, but you know somehow you take the determinant and you get 10. Now what does it look like happened to this determinant to get it to look like this? Now just take it one step at a time. What do you see going on there?
The first and second rows were...
Okay, so at first glance, there's the DEF, there's the ABC. Now you got an ABC and a DEF. So it does look like the first and second rows were switched, doesn't it? Okay, so what would that have done? That would have made it a negative 10. So I'm going to come over here and put the 10 for now, but that first thing, so by switching the A and the D, that negated it. All right, now what else happened?
They multiplied the top row by, they multiplied.
The DEF row by what?
I don't know, because 2 are different.
So maybe I multiplied a row and a column.
Oh, yes.
Because that 10 is really 2 times 5, right?
Yeah.
So it looks like 2, 2, and 2 is in there, 3, 3, and 3 is in the bottom, and then 5, 5, 5 is down the middle.
Yep.
So if I am doing that, I could factor that 2 out, right? It looks like it got multiplied in. So what would that do over here?
So factor the 2 out.
If you did, that would, but it's not. It's already in there. So if I multiply the DEF by a 2, I would have to multiply the 10 by a 2 also, right?
Yeah.
Well, there's a 2 then to account for that.
And then do the 5 on the middle row.
And then 5 on the middle column.
Yeah, that's what I meant.
So that would multiply that 10 by a 2. Well, then I need a 5 because it's in there.
And then the bottom by 3.
And then if the GHI got multiplied by a 3, then that would have been an extra 3.
And then it's.
So I basically had a switched row switched rows, and then a 2 and a 5 and a 3. So what is this equal to?
Negative 300.
So negative 300. Now let me show you a shortcut if you really want to know what happened. Watch this. If you were to do the diagonal method here, what would the first diagonal have been? AEI?
AEI.
And you would have gone on from there, right? Come over here. Which diagonal would have an AEI in it?
It would, you have to switch it.
It's that, and that, right? That's the AE and the I. What diagonal would that have been? That would have been a down diagonal or an up diagonal?
Up diagonal.
Y'all see that? So had I done I would have gone down, 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 and then as I'm going up, I would have hit that one, and the very last one would have been IAE, wouldn't it?
Yeah.
Which makes it negative. So it would have been negative 3I times A times 10E. Are you with me? Which is what?
30 AIE, 30 AEI.
Negative 30 AEI. So I have a question for you. If AEI is 10, then what's negative 30 AEI? Oh, negative 300. That sounds familiar. That's what I got thinking through it the hard way. Are y'all seeing that? Now I kind of cheated a little bit,
Second one.
but does that make sense?
Yeah.
I didn't have to think about the switches and all that junk. I just said, hey, if I did a diagonal, now I would have 6 diagonals in there, but I'm just comparing that first one. Then all of these would be represented kind of like by a 10. Well, if I find that diagonal here, I gotta make sure I get the negative right. It would be going up to hit those, right? If I find that, I can just replace the AEI with whatever it is. And it's a little shortcut to get there. And to me, some of these problems can be really ugly. To me, that might be an easier process on something like this. Are you with me? Okay, this next one I'm going to show you is one of the more common problems that have shown up on math tournaments over the year. And I had this kid named Zach Lindsay. He was a really small, we were kind of first getting started. There was only like 6 kids in the class. And there's this one girl and like 5 dudes, poor girl. She was really shy and timid, and the dudes were just like so out there and rambunctious, and she just kind of got lost in the shuffle, poor thing. But anyway, my best guys weren't at my math tournament one year. And I was down to like, okay, we only had 6 people in the class. And this was like 2001, so we just get started. And I said, all right, Zach, I need you to cipher. He goes, I got you, coach. And that was back before I was, we hadn't done a whole lot back in the day. We were just kind of getting started. I was learning stuff. So, what have you noticed? A lot of these determinants are always equal to? 0. So I told him, I was like, if in doubt, if you get a determinant, 0. He goes, I got it. I literally said that, and he walks up there. First question is pretty tough. Second question, I'm like, I don't know if he's going to get that. Third question, big determinant. And it had this pattern thing going on I'm about to talk about. And I saw it, and I went, sweet. If in doubt, he's going to put 0. And so you know how when you get the problem right, usually they turn around with a thumbs up or whatever. So nothing from him. I'm like, surely, we just talked about this. And I'm sitting here with his friends. And he comes back, and I said, how'd you do? He goes, man, those were rough. I said, what about number 3? I said, you got that right? It was 0. He goes, man, I was feeling 4. I'm like, 4? Why 4? So anyway, needless to say, he missed it. And we didn't do super well, but
Was it 0?
I still have of course it was 0. Yeah, it was this pattern. It was like a super simple one. Well, over the years, in the past 19 years, people have started changing from these super simple patterns and started really testing your knowledge of Gaussian Jordan elimination, the whole 2-row thing. So I want to show you, this is a little pattern that this may have been the problem he had. And you'll see 2, 3, 4, 5, 7, 8, 9, 10, 12, 13, 14, 15, 17, 18, 19, 20. Now what do you notice there? As I move along the row, what am I doing?
Counting up by 1.
I'm adding by 1, and you can see that I am doing that throughout this movement on every single term. Are you with me? Yes? Now what's happening as I go down? I'm adding 5, and you'll see that that's happening on every single term. Whenever that happens, you get 0. Now, why that happens, I want to show you, because the why is critical to helping you get these problems when they're not this clean. The why is this. Check out this problem. What if I were to factor out a negative from row 1? Now, by the way, you don't need to know the why in your test. If you see this, just go, oh, I'm adding 1 here, I'm adding 5 there, equals 0. Okay? Right here. If I factor a negative out of the first row, doesn't it look like this?
Mm-hmm.
If I factor a negative out, everything on the first row is negative. And then what happens if I add the first and second together, because I'm allowed to do that? What do I get? Fives. Now, what if and then I still have the negative sitting there, right? Now, what if I took a negative now out of the second row? Now I have two negatives out there. What happens when I add the second and the third together?
You end up getting two.
Fives
three,
again.
oh.
And you just told me, or we just went over our rule that anytime two of the rows match or are opposites, what is it always equal to?
0.
0 times, in this case, whatever's on the outside, but it doesn't matter, does it? Now I have a question. Did I need the third row to determine, or the fourth row to determine that? I only needed 3. I needed the first 2 to make these 5s, then I needed the second and the third to make those 5s. But I didn't even need this. So what I need you to know is this rule works even if, as long as 3 of the rows or 3 of the columns follow that pattern sequence. Now, if the fourth one does not, doesn't matter. This could have been pie, E, happy face, banana, whatever. Okay? It doesn't matter what that is because I didn't need for that to come into play in order for me to get these 5s. So what do I need you to know? If you ever see a pattern in 3 of the rows or 3 of the columns where you're adding the same thing and then adding the same thing or subtracting, if that happens, always 0.
And that goes for determinants of any size?
Determinants of any size as long as you have 3. So it would work for a 3 by 3, but not a 2 by 2. But a 2 by 2, who needs help with? Right? Are you with me? Actually, does it work with the 3 by 3? Actually, may not. Hold on.
I was wondering what that is.
Not that we need a lot of help with 3 by 3s. If I factor out a negative, 3, 3, 3. I think it does. Then if I factor out another negative and add 3, 3, 3. Yeah, it should. Yep. But you would have to have all 3. The whole thing would have to be patterned there. But as long as you have 3 rows or 3 columns that have those patterns, you're in good shape. And that's more along the lines of what you see. So if you look at this example too, they used to just give them where everything had the patterns, but now they step it up because people learn the tricks and they try to make them a little uglier. Okay, so look at this. Add 2, add 2, add 2, add 2, right? Add 2, add 2, add 2, add 2. Add 2, add 2, add 2, add 2. Add 4, add 5, add 1, add 3. Well, that's off, and this is way off. So the rules work there across. Let's check down. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. As long as any 3 rows or any 3 columns follow that, it's going to be 0. Why? Because of what we demonstrated. But you really don't need to know the why, do you?
Nope.
As long as you have that rule in place. But this is what they do now, and people go, oh, I don't know what to do. Because they've thrown curveballs and not everybody has figured out Gaussian. Because Gaussian elimination is not an Algebra 2 topic. It's a college algebra topic. We talk about it in here, and we talk about it in pre-cal, because I learned it in college, and it shows up. But it's not a topic, it's not a high school topic. So most people don't know it, and then they don't know how to figure these out unless they're just really simple. Okay, now this is what we were talking about yesterday. These are the diagonal ones, right? You don't need any help on this, but isn't it 2 times 5 minus nothing? But look, you've got a diagonal with a 0 below. Multiply the numbers in the diagonal. All right, here's a 3 by 3. Diagonal, down to the right, we're talking about, 0's below. If I were to do it manually, I would get 2 times its minor, right? If I pick this column to expand by, and then to do this, I would get 20 minus nothing. Well, 2 times 20 is 245. Diagonal. I can do this all day. Right here, example 4 by 4, and we did this in class yesterday.
Yeah.
Right? If I did a 4 by 4, I would probably expand by that column. So 2 times its minor. And then I'd probably do this by its minor. So 2 times 4 by its minor. And then to this, I get 5 times 6 minus nothing. So 2, 4, 5, 6. That's just what?
The
The diagonal. So again, all day long, diagonal down to the right, multiply the diagonal. Now, that's if all of them are zeros. On the bottom, all are zeros on the top, or both. You can do it. You with me? If one thing changes, if that number right there becomes an 8, well, I could still go 2 times that determinant, and I could still go 4 times that determinant. But at some point, the diagonal method fails, and I would actually have to do that final little bitty determinant, not just the diagonal. Are you with me? And that's what they do a lot now. So a lot now, they do these big determinants, and they throw a little 8 in there, and people that don't know what expansion by minors is or whatever, they kind of melt and don't know what to do, but we'll be better than that. Right? Okay. Now let's check going up. Okay, so these I actually taught wrongly for a couple of years. I told them, hey, I checked the first 2. All right, diagonal going up. It ended up being nothing minus the 6. Oh, you negated the diagonal. Diagonal going up. If you expand by 2, it's 2 times that minor. And then that minor is nothing minus 36. Oh, so I'm negating the diagonal. And I checked those 2 and went, the rule for coming up is negate the diagonal. And this was probably the same group. And then one of those kids came in and, Mr. Hurry, I thought you said it was just negate the diagonal. I was like, yeah, I did. And they're like, well, I did that and the problem's wrong. And I said, well, you probably just made an error. He goes, no, I checked on my calculator. It's wrong. And I went, no. So I went to the 4x4. And then I noticed this thing. So check this out. On the 4x, now again, we've got rules for 2x2s and 3x3s, right? So a 2x2 or a 3x3 going up to the right, negate the diagonal if there's zeros below it or above the diagonal. Are y'all with me on that part?
Mm-hmm.
Okay, so check out the 4x4. 4x4, if you didn't have any rules, wouldn't you either pick that column or that row?
Yeah.
So let's just say I picked that row. What space is the 3 in?
The first.
A plus or a minus spot? Remember that from expansion?
Plus.
Is it? Plus, minus, plus,
Oh, I
minus.
thought it was like first row plus first.
No, it's like a big checkerboard. Plus, minus, 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 plus, minus, plus, plus, minus, 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 plus, minus, plus. Or you could do it the hard way. What row or column is this? 4th row, first column?
It's 4. I was saying 1 and 1.
So negative 1 to the 5th would be negative. So I gotta negate that 3. Copy its minor down. Now what would you do to do this expansion?
Probably.
Maybe that row again. So I copy the negative 3 over, I copy the 2 over, and I take the minor of the 2 and write it down. And then the minor of that's just 0 minus 35, or negative 7 and 5. But look what happens when I simplify that. The negatives cancel, 3, 2, 7, 5. So what ended up happening?
Positive 2.
But what ended up happening? I just ended up doing what?
You got a positive out of the upward diagonal.
So I didn't change the sign.
Yeah.
So far, I know that if it's a 2x2 or a 3x3 and it's going up, I negate the diagonal, right? And I just found that if it's a 4x4, I don't negate the diagonal. Well, let's look at a 5x5. Now, hopefully, you can start taking a shortcut like this without doing all the work. Couldn't I have just said, hey, I already know that a 3x3 going up does what?
It's negative.
Negates the diagonal. And if I already have a negative 3 out front, what ends up happening?
It becomes
Positive. So let's do that same thing with a 5x5. If I see the diagonal, and it's got all these zeros, I could go 6, and by the way, 6 is in a plus, minus, plus spot. 6 times that 4x4 minor. But I already have a rule for 4x4 minors. What's my 4x4 rule coming up?
It's positive.
So I just take the diagonal. So I'm going to take the 6 times the diagonal. And I don't change any signs because I don't change signs with 4x4s. Doesn't that give me 6, 3, 5, 2, 10? And again, what did I do?
You didn't.
I didn't negate it. So for 5x5s, I'm proving these rules. I don't have to negate it. Now, what would happen if I went to a 6 by 6?
Then you just, like,
I'll show you, but anybody got a guess? Anybody can tell me why?
wait, but if that 6 was a negative 6.
But it's not, it's in a positive spot.
But
Plus
no,
minus.
but like if it was a negative 6, like if it was 2, 6, 4, 6, negative 6.
And then, yeah, you would have just taken that number and brought it over here, but you would not have changed the signs. But if that was a negative 6, I'm still not negating the diagonal. That was
Yeah,
just
yeah.
one of the numbers that was in there.
I got you.
And I'm glad he brought that up. I'm avoiding that so it's very clear right now what I'm doing. And I'm not throwing extra negatives in there to confuse you. But yeah, if all these numbers were negatives, they would all have negatives there, but I wouldn't be doing the extra duty of negating the diagonal, would I?
Mm-hmm.
Now, what would happen on a 6 by 6? Let me just try to make this into a 6 by 6. So what if I extend it, and let's say this is a 2 right there. 5, negative 1, 3, 7, 8. So this is now a 6 by 6. Are you with me?
Yeah.
So what would I have done here? I would have probably chosen that row again. Now 2 is now in a what? Plus, minus, plus, minus, plus, a negative spot?
Negative spot.
So I would have had a negative 2, ignore this. I would have a negative 2 times its minor, correct?
Mm-hmm.
Now its minor would be what size?
5 by 5.
And I already have a rule for 5 by 5s, right?
Positive.
So for 5 by 5s, I don't change the diagonal. So I'm going to be going negative 2 times the diagonal. And what does that mean? I do what? There's no negative with that 2. So what did I end up doing? Negating the diagonal. So for a 6 by 6, I end up negating the diagonal. Guess what happens on a 7 by 7? It's still negated. Guess what happens on an 8 by 8? Not negated. 9 by 9, not negated. 10 by 10, negated. And I wrote all this down, but right here, when the diagonal comes up, it's just a pattern. 2 by 2s and 3 by 3s, negate the diagonal. 4 by 4s and 5 by 5s, do not. 6 by 6s and 7 by 7s, negate the diagonal. 8 by 8s and 9 by 9s, do not. You're with me? And it alternates every 2 like that. Guess what the biggest mistake is with students? They forget and they want these rules down. They write 1 by 1s and 2 by 2s, negate. 3 by 3s and 4 by 4s, don't. But a 1 by 1, not much of a determinant, right? So remember that if you start writing these rules out, which I promise you I'm not going to give you, I'm probably going to give you a 10 by 10 or a 13 by 13. And I'm usually pretty nice on the diagonal. Like, why is this diagonal pretty nice? Because it's easy to multiply by a 10, and 2 and 5 make a 10. So it's pretty easy to go, oh, 18, 10 and 10, 1800. So I do a lot of that, but I'm checking to see, do you know, because this is a 5 by 5, that I do not negate this diagonal. There's no negative out front to change the sign, because you don't do that with 5 by 5s. So coming down, pretty easy, just multiplying. Coming up, you got to know that pattern sequence. And I'll give you practice on this. If you do the homework, you'll see these and catch it. All right, last thing, well, maybe not last thing, because we'll go through some practice problems. Well, we'll try, because we only have 5 minutes. Who knows how to find an inverse of a 2 by 2?
We
We just did it, right? We know how to do that, right? Who knows how to find an inverse by a 3 by 3? Only me. They're not that hard. Actually, they're not easy. It's like a 4-step process. We're not going to learn that here unless maybe we have some time and they actually have a state term, because that's the only reason we would need it for the work that we're doing in Algebra 2. If, however, they'll ask this question. They'll say, find the determinant of the inverse of this. Now, English, if you read the English correctly, what is it asking you to do if it says find the determinant of the inverse? Sounds like they're asking you to do what first? Find the inverse, and then once you get that inverse, take the determinant of it. Problem is, you don't know how to find an inverse. And guess what? Let me show you. Here is a let's pretend that's a matrix. What if I said find the determinant of this inverse? Well, I can find the inverse of this. What is the inverse of this thing?
4, -5, 3.
Switch that. Negate those. Probably should have thought about this answer. And then 1 over the determinant, which is 21 what? I tell you, make it a positive 4.
21.
Make it a positive 4. Now what is it? 21 minus 20.
1.
So the inverse ends up being, I'm trying to make it simple, ends up being this. So if my question was find the determinant of the inverse, what is the determinant of this?
21, so 1.
1. I found the inverse. No, I hate that it's 1.
Well, it's just whatever number.
Hey, do this for me. My example is going to be crap, but anyway. My point is finding the inverse and then taking the determinant of the inverse gave me a value. It just so happens finding the determinant and then doing the inverse gives you the same answer. The only difference is when you find the determinant, what does it give you?
It gives you the.
What do you get when you do
You
it?
get the denominator in the thing.
Well, hold on. When you find a determinant, just a determinant, what do you end up with? On every determinant you've done, you end up with a what? Just a number. So if you end up with a number, how do you take the inverse of a number?
You
get a reciprocal.
You just take a reciprocal. So it turns out the determinant of the inverse is the same thing as the inverse of the determinant. And that I can do, because I can take the determinant of that. The only difference is when I take the determinant, I get a number like this, 31. And now to take the inverse of a 31, well, the only way to take an inverse of a 31 would be a multiplicative inverse, and you flip it. They put this question at tournaments all the time because people go, I don't know how to do the inverse, and then they move on. And if you don't know this trick, that the determinant of the inverse is the inverse of the determinant, you wouldn't be able to get it until you learn how to do an inverse. And even if you did, it would take you forever because the rules are really ugly. So what you would do, if I gave you that, is you'd remember that rule and go, all right, you do the diagonal method, expansion by minors, you finally get to 31, and you just flip it. You see that? And I've asked that on every test I can remember. All right? So in the time we have left, and you just do whatever way you can. I would do all of these, honestly. I don't know if we'll get to all of them in class, probably not, but let's see if we can race through them. Anything you see on this first one that might be of help to you? It's a 3x3, and you know you can do 3x3s. If you see anything that might be helpful,
They all have like.
maybe take some junk out. I don't see anything I like, but what if I said, how about factoring a 10 out?
Should be 1, 7 there too.
That would be a little helpful. It's still some big numbers. Anything else you can see comes out?
Factor 5 out of the middle.
5 out of the middle. That's making it look better.
7, 4.
Anything else?
I think can you pull it 31? Yeah. So.
You can pull a 13 out of the bottom.
So -1.
-1, -7, 2.
Take a 7 out of the middle.
Oh wait, what do I have on the top and the bottom row?
You have a 7 on the middle one.
That's
and a
true, but what
2.
do I have on the top and the bottom row? They're opposites. What happens when any two rows are opposites?
You can add them together and replace.
You could, which would give you zeros, but what do you know that determinant is if they're opposites?
It makes it a 0.
It makes it a 0. What's 0 times anything? Look, I didn't even have to do that determinant. What about number 2?
You can take 12.
Yeah, and I don't think when you take stuff out of that, you're gonna get a 0, maybe you do, I forget. But at least you could get some of the junk out and make it more doable, right?
Yeah.
Let me look at something else. What about number 3?
Oh, nice. Looks like some symbols.
What would you expand by?
0.
Yeah. What about number 4?
You
It's a
go-
5x5.
So it's a positive.
4x4 and 5x5, you don't change the sign, do you? So just the diagonal, 8.
8.
Y'all seeing these? What about number 6? It's a 4x4,
But it's
so don't negate it, right? -120 over it. What do you see on number 5? And you can go if you gotta go.
there's opposites and the top and third there's opposites.
And if they're opposites,
it's a 0.
it's a 0. So check these out, see what you can do, bring questions if you still have them.
So 2 rows or 4 columns are opposites? Zero.
Opposites or the same. Correct. Yeah, because getting them together just pulls a negative out. Like if I switch these two, it pulls a negative and then they're there, but it still ends up being 0 times a negative, which is 0.
Thank you.
Yeah.